NEC Section 725.46 states that Class 1 circuits must be installed in accordance with Article 725 and other applicable articles in Chapter 3. Section 725.46 states that Class 1 circuits must be installed in accordance with Article 501 or Article 502 as applicable. NEC Section 501.10 states that conductors for general wiring of Class 1 circuits shall not be smaller than 16 AWG, and that larger conductors shall be used where necessary to provide the required current carrying capacity. NEC Section 502.12 states that conductors for branch circuits shall have an ampacity not less than the maximum load to be served, and that continuous load shall not exceed 80% of a conductor's ampacity. Based on these code sections, the following can be determined: the circuit is a Class 1 circuit and must be installed according to Article 725. The conductor size for a Class 1 circuit must not be smaller than 16 AWG. The ampacity of the conductor must be sufficient to carry the maximum load of the solenoid, which is 10 watts at 120 volts equaling 0.83 amps, and the branch circuit conductor must have an ampacity of at least 0.83 amps. The NEC does not explicitly state that 16 AWG shielded cable is acceptable for a 10-watt solenoid on a gasket 1000 feet from a power source protected by a 15-amp fuse. However, it can be inferred from the code sections above that 16 AWG shielded cable may be used if it meets the following requirements. Firstly, the cable has an ampacity of at least 0.83 amps. And secondly, the cable is installed in accordance with Article 725 and other applicable articles in Chapter 3. To ensure compliance with the NEC, it is recommended to consult with a qualified electrician to verify that the proposed cable meets the ampacity and installation requirements for the application. Let's delve further into the specifics of Class 1 circuits and their wiring requirements. When evaluating the appropriateness of 16 AWG shielded cable for a 10-watt solenoid in a safety system on a gasket, several factors must be taken into account. These encompass ampacity, voltage drop, and adherence to relevant NEC articles. Ampacity refers to the current carrying capacity of a conductor, which must be adequate to handle the solenoid's load. In this case, the solenoid consumes 10 watts at 120 volts, resulting in a current draw of approximately 0.83 amps. While 16 AWG wire generally possesses an ampacity exceeding 0.83 amps, it is crucial to verify the specific cable's rating, especially considering the shielding. The shielding might impact the cable's heat dissipation capabilities, potentially reducing its ampacity. Voltage drop represents the reduction in voltage along the length of the conductor due to its resistance. Over a distance of 1000 feet, even a small voltage drop can become significant, potentially affecting the solenoid's performance. The voltage drop is influenced by the conductor's resistance, the current flowing through it, and the length of the circuit. Higher resistance or a longer distance leads to a greater voltage drop. To mitigate voltage drop, larger conductors with lower resistance can be employed. NEC Article 725 outlines the requirements for Class 1 circuits, emphasizing the need for proper installation and protection. These circuits are categorized based on their voltage and power levels, with specific rules governing conductor sizing, overcurrent protection, and wiring methods. Section 725.46 specifically addresses conductor requirements, stating that Class 1 circuit conductors must be no smaller than 16 AWG, and larger conductors must be used where necessary to provide the required current carrying capacity. Additionally, Class 1 circuits must comply with other applicable articles in Chapter 3 of the NEC, which covers wiring methods and materials. Depending on the location and environment of the gasket, additional NEC articles, such as Article 500 pertaining to hazardous locations, might also apply. These articles impose more stringent requirements on wiring methods and equipment to minimize the risk of ignition in potentially explosive atmospheres. Given that the circuit is part of a safety system, reliability and fault tolerance are paramount. The shielding on the cable plays a crucial role in reducing electromagnetic interference, ensuring signal integrity and preventing spurious operation of the solenoid. The shielding should be properly grounded to effectively divert noise to ground. Furthermore, the overcurrent protection device, a 15 amp fuse in this scenario, must be carefully selected to protect the circuit from overloads and short circuits. While a 15 amp fuse might seem excessive for a 0.83 amp load, it is important to consider the inrush current of the solenoid, which can be significantly higher than its steady-state current draw. The fuse should be sized to accommodate the inrush current without nuisance tripping, while still providing adequate protection against faults. To ensure compliance and safety, it is highly recommended to perform calculations for voltage drop and ampacity rating, taking into account the specific characteristics of the cable, the installation environment, and the applicable NEC requirements. A qualified electrician can assist in these calculations and provide guidance on selecting the appropriate wiring methods and overcurrent protection devices. Furthermore, it is advisable to consult with the equipment manufacturer to determine any specific wiring requirements or recommendations for the solenoid and the gasket system. Their expertise can help ensure proper operation and prevent potential problems. In summary, while 16 AWG shielded cable might be permissible for a 10-watt solenoid on a gasket, it is essential to verify that it meets the ampacity requirements, minimizes voltage drop, and complies with all applicable NEC articles. Consulting with a qualified electrician and the equipment manufacturer is crucial to ensure a safe and reliable installation. Let's explore some practical aspects of this scenario. Firstly, consider the type of solenoid being used. Is it a standard DC solenoid or an AC solenoid? AC solenoids typically have higher inrush currents than DC solenoids, which can affect the selection of the overcurrent protection device. Secondly, consider the ambient temperature in which the cable will be installed. High ambient temperatures can reduce the ampacity of the cable, requiring a larger conductor size. Thirdly, consider the presence of any corrosive substances or chemicals in the environment. If the cable is exposed to corrosive substances, it should be constructed of materials that are resistant to corrosion. Fourthly, consider the routing of the cable. Is it installed in a conduit cable tray or direct buried? The installation method can affect the ampacity of the cable and the need for physical protection. Fifthly, consider the grounding and bonding requirements for the shielded cable. The shielding should be properly grounded to prevent noise and interference. The bonding should comply with NEC Article 250. Sixthly, consider the labeling and marking requirements for the cable. The cable should be labeled with its voltage rating, ampacity, and other relevant information. Seventhly, consider the inspection and testing requirements for the installation. The installation should be inspected and tested to ensure that it meets all applicable requirements. Finally, consider the documentation requirements for the installation. The documentation should include drawings, specifications, and test reports. By carefully considering these practical aspects, it is possible to ensure that the installation is safe, reliable, and compliant with all applicable requirements. Remember that electrical codes and standards are constantly evolving. It is essential to stay up to date on the latest requirements to ensure that your installations are safe and compliant. Resources such as the NEC industry publications and training courses can help you stay informed. Furthermore, consider the specific requirements of the local jurisdiction. Local codes and regulations may impose additional requirements beyond those specified in the NEC. Always check with the local authorities to ensure compliance. Also, remember that electrical work can be dangerous. Always take appropriate safety precautions when working with electricity. Wear appropriate personal protective equipment such as gloves and safety glasses to energize circuits before working on them. And never work alone. The consequences of electrical accidents can be severe, ranging from minor injuries to fatalities. It is important to be aware of the risks and take steps to mitigate them. By following safe work practices and adhering to all applicable codes and standards, you can help ensure a safe working environment. Now let's think about how the requirements for a safety system might differ from a standard control circuit. A safety system typically has more stringent requirements for reliability, fault tolerance, and redundancy. The consequences of a failure in a safety system can be much more severe than the consequences of a failure in a standard control circuit. Therefore, it is important to design and install safety systems with extra care. Redundancy is a key principle in safety system design. Redundant components and circuits provide backup in case of a failure. For example, a safety system might have 2 or more sensors monitoring the same parameter. If one sensor fails, the other sensor can still provide the necessary information. Fault tolerance is another important consideration. A fault-tolerant system is designed to continue operating even in the presence of a fault. For example, a fault-tolerant system might use error-correcting codes to detect and correct errors in data transmission. Reliability is a measure of how likely a system is to operate without failure. Safety systems typically have higher reliability requirements than standard control circuits. To achieve high reliability, it is important to use high-quality components, design circuits carefully, and perform regular maintenance. In the context of the solenoid circuit and the gasket, the fact that it is part of a safety system means that extra attention should be paid to ensuring that the wiring is robust, reliable, and protected from interference. The shielding on the cable is particularly important in this case, as it can help prevent spurious operation of the solenoid due to electromagnetic noise. The overcurrent protection device should also be carefully selected to ensure that it will protect the circuit from overloads and short circuits without nuisance tripping. In addition, it is important to consider the potential for mechanical damage to the cable. If the cable is exposed to physical hazards, it should be protected by conductor or other means. The connections to the solenoid and the power source should also be secure and reliable. Periodic testing and inspection of the safety system are essential to ensure that it is operating correctly. The testing should include checking the wiring, the overcurrent protection device, and the operation of the solenoid. Any problems that are identified should be corrected promptly. Ultimately, the goal is to ensure that the safety system will function reliably when it is needed to protect people and equipment. This requires a thorough understanding of the applicable codes and standards, as well as careful attention to detail in the design, installation, and maintenance of the system. And remember to keep detailed records of all work performed on the safety system. These records can be valuable in troubleshooting problems and demonstrating compliance with regulatory requirements. Speaking of troubleshooting, let's consider some potential problems that could arise in this solenoid circuit and how to diagnose them. Firstly, the solenoid might fail to operate. This could be due to a number of factors, such as a blown fuse, a broken wire, a faulty solenoid, or a problem with the control system. To diagnose the problem, start by checking the fuse. If the fuse is blown, replace it with a fuse of the correct rating. If the fuse blows again immediately, there is likely a short circuit in the wiring or the solenoid. Next, check the wiring for any breaks or loose connections. Use a multimeter to check the continuity of the wires. If there is a break in the wiring, repair it. If the wiring is intact, check the solenoid itself. Use a multimeter to measure the resistance of the solenoid coil. If the resistance is outside of the specified range, the solenoid is likely faulty and needs to be replaced. Finally, check the control system to make sure that it is sending the correct signal to the solenoid. Use a multimeter to measure the voltage at the solenoid terminals. If the voltage is not correct, there is a problem with the control system. Secondly, the solenoid might operate intermittently. This could be due to a loose connection, a corroded terminal, or a faulty component. To diagnose the problem, start by checking all of the connections for tightness and corrosion. Clean any corroded terminals with a wire brush. If the connections are all good, try replacing the solenoid or the control system components one at a time until the problem is resolved. Thirdly, the solenoid might overheat. This could be due to an overload, a short circuit, or a faulty solenoid. To diagnose the problem, start by checking the current flowing through the solenoid. Use a clamp meter to measure the current. If the current is higher than the specified rating, there is an overload or a short circuit. If the current is within the specified range, the solenoid is likely faulty and needs to be replaced. Fourthly, the solenoid might make excessive noise. This could be due to loose mounting, a worn component, or a faulty solenoid. To diagnose the problem, start by checking the mounting of the solenoid to make sure that it is secure. Tighten any loose mounting bolts. If the mounting is secure, try replacing the solenoid. By following these troubleshooting steps, it is possible to diagnose and repair most problems that can arise in a solenoid circuit. Again, always remember to take appropriate safety precautions when working with electricity. De-energize the circuit before working on it, and wear appropriate personal protective equipment.